The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Today we have two guest lecturers. The one I invited is Professor Peter Furth. He's an expert on transit signal priority. He's done work on reliability buffer time, and sort of how people budget for their travel times. Really good paper on that. And he's also a bike expert. He's really interested on bicycles. So that's not today's topic. Maybe you get him off sort of out of class and ask him something. Then we also have, he dragged someone else in from the Netherlands, who also knows a lot about transit signal priority. So I don't really know what to say about him, but I'll find out. Maybe you can introduce him.
Yeah, I'll introduce him. Yeah, okay. Hi all, thanks, it's great to be here. Just a little bit, before I get into transit priority, I just want to tell you a bit more about my background. So as I studied here at MIT, and my focus was on public transportation. Then I became a professor at Northeastern, and after several years, for one thing, there weren't enough jobs in public transportation. My students needed more training in traffic engineering because there were more jobs in that. But then the other thing is that our buses were getting stuck in traffic all the time, and I wanted to learn, well, can't we figure out a way to make the lights turn green for a bus? I mean, if we can get a man on the moon, surely we should be able to get the lights to turn green for a bus. So I got the chance to go to the Netherlands for a year, a sabbatical year, and almost did a second PhD there, studying traffic signal control for transit priority. I mean, so you have to learn all of traffic signal control, and then you can learn, okay, and now how do you do transit priority? Then I came back to the United States, and it took me several years to try to figure out how the Dutch traffic signal control, they use different language, but it's really about the same. There are some differences, but it's mostly the same. How to say that in American traffic signal control. And since then, I've done a lot more work now in traffic signal control and transit priority. So that's how I come here. My title is it help or is it hype? And I really mean that because if you go to Zurich, transit signal priority is real help. I went there once on an official visit, and I told the people I was visiting, I came here because I've heard it said that the trams never have a red light. He said, yeah, well, that's just about true. There are some exceptions, he said. Oh, of course, like at the main square, there are so many trams. They come from different directions. So one tram has a red light for another tram. But otherwise, there are only one or two intersections in the whole city where the trams don't just get a green light. I learned that in Portland, when they designed their light rail in the 1980s, station to station green waves are programmed into the traffic signal control. Now, it doesn't mean zero delay, because what that means is when a light rail train is at a station, there'll be a countdown clock for the driver. So there's no point in leaving now because you're going to have a red light. But if you wait until the appointed time to leave, then you will have a green wave to the next station. But then we come to applications of transit signal priority in the US. And if you hear these great pronouncements, oh, we're doing transit signal priority. But when you look into it, there's almost no benefit. Sometimes they're saving the bus 2 seconds per intersection or less. Often they're not measuring at all. So then I have to ask, is it really a help or is it hype? And I will tell you, so what I'm going to tell you today is some of the standard ways of doing transit signal priority, how they work and how they don't work very well. What we have to do to really be able to have our buses or trams have nearly zero delay. So before we get into the detail, why are we doing transit priority? This is a class on public transportation, so it probably doesn't need a lot of argument. But we start with a societal objective. Transit offers many benefits to society in terms of congestion, air quality, livable communities, and so on. And transit is mostly competing with car use. And what transit can do is break the vicious cycle. And there's a vicious cycle, and this is especially strong in developing countries, where as people get more money, one of the first things they want to buy when they have more money is a car. And then with the car, the roads become congested, and then that slows down transit, so then people don't want to use transit, so then they get more cars, and it just keeps going. If you can do priority for bus, then that breaks that cycle, and now people will say, I'm going to use the bus or the train to have priority. And then having priority for transit makes a lot of sense, because the tradition in Boston has been a very extreme all-or-nothing priority. We know one way to give transit priority: total grade separation. We build a subway, and they're protected from congestion. So we know how to do the $2 billion priority, and we also know the other extreme, which is nothing. Buses, you're welcome to use our roads. I mean, you know, when the light turns green, everybody else can go. I guess you can too. It doesn't make sense to only have those two extremes. And that's what the city of Zurich did. They were the main planners for Zurich wanted to build a subway. This was in the 1970s. Big cities were starting that didn't have subway systems then were building them. But the citizens said, no, spend a tenth of the money, because subways are incredibly expensive. Spend about a tenth of that money to make our trams, give our trams priority. And then we don't have to walk down in the basement, and instead we like how the trams are right. It's almost like an extension of the sidewalk. You just step on, ride, step off. So it makes sense to have some means of priority that's in between all or nothing. And we have two ways of doing priority. It's priority in space. That means you give the buses or the trams their own lane, their own space. And then there's priority at time, which comes at traffic signals. Priority, it's easy to see what it means to a transit user. It means you get a faster ride and a more reliable ride. So it saves you time. It also, the reliability means it also saves you in buffer time. But it's important to know what transit priority means to a transit operator. The savings in time means they might be able to run their route with fewer vehicles and less labor. And the improved reliability means they don't have to have as much recovery time. So in Portland, they had a case at TriMet line 12. It didn't the transit priority they put in didn't reduce the running time that much, but it reduced the variability of running time so much that they were able to reduce the cycle time by 11 minutes. And if you reduce the cycle time by 11 minutes on a route that runs every 11 minutes, then you save one bus and one operator, and that lowers your cost tremendously. So priority is important for passengers, it's important for the operator. And when I told you I studied traffic signals in the Netherlands, and it was in the context of transit priority and how can we make transit service better. So here you have two graphs of each line represents the trajectory of a vehicle. On the bottom is space. We're going from station CL across to station S. And on the vertical axis is how far off schedule are we. So if you're at the 0 line, that means you're perfectly on schedule. And as you go above the line, you're earlier and earlier. And as you go below the line, you're later and later. So this is what the operation was, kind of, if you just let it be. The buses would start pretty close to on time, but they got later and later and later, and the spread just gets worse and worse and worse. This is nothing new. If you know about transit service, you know how there's these random shocks could make a bus late, and once you're late, you become later and later and later, and once you're earlier, you become earlier and earlier and earlier. But here, they put in a system with priority at the traffic lights, and it's conditional priority. It's if the bus is early, no priority for you, but if the bus is late, we're going to give very aggressive priority so that bus can cruise right through the intersection. So if the average time to get through an intersection is, let's say, half a minute, but with priority, that's going to be 10 seconds, and without priority, that's going to be 50 seconds. That's a 40-second difference that I can make my bus like kind of 20 seconds later by not giving it priority. I can make my bus 20 seconds earlier by giving it priority. So with that, you see how much tighter the lines are, how much better the reliability is, because the priority system is able to keep those buses right on schedule. Yeah.
Doesn't this annoy the people driving on the road who have to use that traffic light, and they know it normally takes them 30 seconds, and all of a sudden it's 50 seconds? Or is this some kind of separate light?
No, this is not let's hold the light red extra long. This is just we won't give priority. That's all. So when I say we won't give priority, I'm not talking about holding. So we're not deliberately holding the light red. It's just if the bus arrives and the light is green, okay, bus, you get to go through. But if you arrive when it's red, I'm not going to hurry up and turn the light green for you if you're early. I'm only going to do that if you're late. And priority makes transit more competitive because, after all, transit has to stop to pick people up. That slows it down. You have to walk to get to the station. That adds more travel time. How can we compete with car? Well, one way we can compete is we can give transit priority, and it makes it more acceptable. And because I got late, don't get to tell you the story about my great aunt. So there are different levels of priority. One of the things you'll often hear, if you ever hear a presentation about priority, they'll say it's not preemption. Preemption is a technical term in traffic signal control, and preemption is what we'll do for a fire truck. And that just means, preempt the signal, just stop. Every conflicting movement goes to yellow, goes to red, and we just stop everything so the fire truck can go through. And by the way, the street that the fire truck is on, we don't turn that one red. We make that one green. So the fire truck, it's not like we ask everybody to pull over out of the way of the fire truck. We ask everybody to just keep driving, go, 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 go. We give them a green wave, go, 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 and then the fire engine comes along. So that's preemption. We do that for fire engines, and we do that for trains, because trains can't brake. When you get a train coming along at 40, 50 miles an hour, trains that steel wheel on steel rail, they can't brake very quickly. So we will preempt a light for a train. So priority is something short of preemption. For instance, with transit priority, we will not cut off a pedestrian phase. Pedestrians there's a certain clearance for pedestrians to be able to cross the street. You've seen the countdown signals. So for a fire engine, it could be 15, 14, 0. But we won't do that for transit. And preemption is it doesn't think a moment about the impact on the other traffic. We got to save a life. Somebody's life is at stake. Somebody's house is burning down, and there's a train coming that would kill everybody in its way. So when it comes to saving a life, you don't worry about, is it costing people a few extra seconds, minutes of time. But transit priority, if we're going to give priority to transit vehicle every 5 minutes, every 3 minutes, you can't be completely disrupting and screwing up traffic every 3 minutes. You have to think about how it affects others. So there are some standard tactics. The main ones I'll talk about are listed here: green extension and early green. But I'll also talk about some more intelligent tactics and some ways of changing the background. So let's look at at the most popular tactic, which is green extension. Green extension means the street that the bus is on, the light is green. It's about to turn yellow. But we detect, there's a bus coming and it's only 12 seconds away. All right, then we'll just delay turning yellow. We'll just extend the green. And then the bus will come right through, and then the light can turn yellow and turn red. So That offers, as I have there on the slide, a very large benefit to the buses who take advantage of this. I mean, because the bus who gets the green extension, that's the bus that if they didn't get that extension, they would arrive right near the beginning of red, and they'd have the longest wait of anybody in the cycle. They have to wait the whole red period until they can finally go out. So if the red period is 70 seconds long, you just saved that bus about 70 seconds. So it's a very large benefit. But it's a benefit only to a few buses. Because which buses get to enjoy that benefit? Only the ones arriving during the first few seconds of red. Let's say you're willing to give a 15-second green extension. Then any bus arriving in the first 15 seconds of red, that gets a benefit. But if the cycle is 100 seconds long and buses arrive at random, well, that's only 15% of the arrivals that are in that window. So green extension is a large benefit, but to a small number of buses. And we can model that benefit this way. On the horizontal axis is time in the cycle. And on the vertical axis, I have arrivals, and so you have cumulative vehicles arriving. And then the red lines going across, that's, are you raising the question? Yeah.
So about that, you said it's a large benefit to a small number of buses.
Yeah.
Per intersection, because if the whole bus route has 10 or 20 signalized intersections, then over time, the probability of every single bus enjoying that, every single bus that runs, I mean,
sure.
Yeah, you say it's only 15% of buses. It's actually a lot more, and it's
So let's say 15% of bus arrivals at a signal.
at a signal, but
Yeah.
over a lot of signals.
Yeah, if I'm running a route in which I'm going through 20 signals and I'm going to get the benefit of 15% of them, on average, I'll get that benefit. Well, that would be 3 times, 15% of 20. Yeah. So the red lines here represent the time that a person is in the queue. So like the car arrival, here's arrival number 1. And then this line is the departure curve. Cars arrive at a relatively slow rate, let's say 1 car every 5 seconds, and they pull out at a much faster rate, say 1 car every 2 seconds. So each horizontal line represents a certain vehicle that has arrived. So let's say the vehicle number 2 arrives here, and vehicle number 2 doesn't depart until here, so that horizontal line is the waiting time of vehicle number 2. So in this representation, horizontal distance is waiting time. So for the bus with a green extension, instead of red starting at time 0, the red actually doesn't start until here. So a bus that would have arrived and been delayed, now that those buses aren't, buses that arrive after the extension time still are delayed. So the possibility for delay, which is represented by the red area, there's less of it, and you find the average horizontal length average horizontal length between these lines, and then you do a little bit of geometry, and we find that the expected delay in the first case, this is a standard delay for cars. It has to do with the length of the car, the cycle length, c, and the ratio of the arrival rate to the discharge rate. That's v over s. And when we put in a green extension, we have that same term minus this term here, and I give that the name the priority push. So that's the reduction in delay thanks to green extension. And that reduction in delay has to do with how long an extension are you willing to give. In some places, they say, well, I'm willing to extend for 10 seconds. In Toronto, they often say, I'm willing to extend for 30 seconds. So it depends on how long is your extension. But it also depends a lot on how long is your red and how long is your cycle. So just so you can have some numbers of, oh, yeah.
Sorry, in the previous slide, why is the border between red and green slanted up?
So this is this slanting, this line here. Okay, so that represents the cumulative departing cars. Okay, so at a certain point in time, the light turns green, and then the first car departs. The second car doesn't depart until about 2 seconds later. The cars follow one another. So this line has a slope of about 1 car every 2 seconds as they depart. This is as they arrive. It's maybe 1 car every 5, 6, 7, 8 seconds. Okay? And where the 2 lines meet, that means the last car in the queue is now gone. And after that, as cars arrive and depart without any queue, without any joining a queue, they just go through. So to put some numbers on that priority push, let's consider a sort of typical intersection with a cycle length of 100 seconds, 50 seconds of red time, and the V over S, that V over S term is such that the degree of saturation is 85%, that's pretty typical. So this shows how the priority push varies with the green extension. The longer an extension you're willing to give, the more of a priority push. But notice they're not equal to each other. For instance, when the green extension is 15 seconds, that gives me a priority push of about 8 seconds. So often, if anybody does try to describe the priority tactics they're using, they'll say something like, oh, when we give 15-second green extension. Well, that doesn't mean it's going to speed the buses up by 15 seconds. In this case, it would, how it affects each individual bus varies, but on average, that will reduce the delay of buses. This is averaged over all buses. Reduce the delay by 8 seconds. And then it has a lot to do also with the cycle length. So let's again consider a 100-second cycle, degree of saturation 85. This time, hold the green extension period fixed to 15 seconds and look at different amounts of red time. So if your red time is low, that's like the bus is on the through road that gets green most of the time. We're green most of the time, and only a small part of the cycle is for the cross street. Well, then the priority push is pretty small, only about 5 seconds. But if the red time is long, if it's a 100-second cycle and the light is red for you 90 out of those 100 seconds, well, then getting pushed ahead 15 seconds will save you a lot. Now, when is the light red for 90 out of 100 seconds? Under what kind of traffic movement would it be that is red almost all the time with a very short green? Yeah.
Maybe like a city center pedestrian plaza?
No, probably not, because if you only give the cars 10 seconds, you just can't get much traffic through, yeah?
D Street in South Boston.
Oh, you got it. You got it. But that's not a typical case.
The cross streets of a major thoroughfare.
So the cross streets, even they get more like 25 seconds.
Like a protected left.
A left turn. That's it. This is the one that really, really could benefit from a green extension. So so right next to Northeastern is Ruggles Station, and you got all these buses making left turns. And if they don't make it, sorry, 120-second cycle, 100 seconds of red. So that's a situation where a green extension would be, it's valuable in all these cases, but it's especially valuable when there's a really long red time. So I'm glad you mentioned D Street. I'll be talking about D Street. All right. Okay, how do we do detection? Technically, to detect a bus, it's almost trivial. There's so many different ways to do it. I'll say something about technologies, but where do we want to detect the bus? So we want to have a check-in detector, so the bus reports in, hello, I'm a bus. Can you give me priority? And there's a trade-off. We'd like to, the sooner we know, the better, because then we can prepare for it and get that light to be red. But if we know, you tell me 2 minutes in advance there's a bus coming, bus travel time is not deterministic, right? So there might be stops in between, and random dwell time. There might be other traffic signals in between. So usually we don't want our check-in to be we want our check-in to be as far away as can be, but no farther than the next stop or the next intersection. So there's a pretty deterministic travel time. We also want there to be a checkout detector. Some systems omit the checkout detector. So if you omit the checkout detector, here's how inefficient you are. You say, oh, there's a bus coming. I'll give it a 15-second extension. The bus goes through after 3 seconds, and you still hold a light green for the full 15. That doesn't make any sense. So have a checkout detector. As soon as the bus hits that, you cancel the extension request, let the light turn yellow. The traditional technology for extension is we bury in the ground a loop, not just a dumb loop, a cable, but a loop that acts like an antenna. So the bus is coming along, giving along a very low energy signal. I'm bus number 2356, so you can check my ID to make sure that this is not a stolen unit. And it could give off some information like, I'm turning left, so I need the left arrow. There's another bus route coming along that's going straight. So you got this. That's one way of doing it. Nowadays, we'll be doing it with GPS. So, and basically cell phone technology, texting. The bus sets up text messages with the controller, and says, "Here are my coordinates. Here are my coordinates," and just keeps sending essentially little packets of cell data like text messages. And then we know where the bus is, and we can take action. So I can skip that. One difficulty of giving priority is, well, what if there's a near side stop? If you looked at locating stops for buses, there's a basic choice between the near side, the upstream side of an intersection, or the far side. Well, if you're on the near side, remember, stop dwell time is random. So I don't even want to check the bus in until it's left the stop. Well, that means my check-in point is going to be awfully close. So what? I'm going to find out 2 seconds before the bus comes that a bus is coming? If you only have 2 seconds advance notice, how long a green extension can you give?
2 seconds.
2 seconds. Think about it. You can't give a 15-second extension if you're only detecting the bus 2 seconds early, right? If I was gonna end the green at time, let's just pick a number, at time 50, and I say, oh, I'm willing to wait till time 65, but I don't know the bus is there until time 63. How would I know to extend the green? Yeah, you cannot give a green extension longer than the advance notice that you have. So this is a killer. Yeah.
I'm just curious about the actual mechanics of the signal extension.
Yeah.
Is this a signal you're sending to just that one traffic intersection? Or are you sending a signal to some central control that's controlling the whole city's traffic lights?
A single place. Now, it can work through the central place, but I'm talking about, buses detected for a particular light. Hold that particular light green for me. It doesn't do anything to any other intersection.
Oh, what I meant was, does it send a signal to some central control, which then tells that light to change?
That's an option.
Okay.
So, in Zurich, yes, they do that. But man, you need all kinds of cabling for that. In Zurich, the controllers on the street are 100% slaves. All they do is when the central computer tells them to change from green to yellow, they just say yes. And the only other software they have running in them is some kind of checking to make sure that they're not violating something. But that's not the tip. That's a very unusual setup that was done ages ago. Nowadays we have very reliable microcomputers in the controllers. So the central computer will make sure every intersection is on the clock. Every intersection is supposed to have its certain offset. You turn green a certain time in the cycle. And it will give them the basic parameters 30 seconds for this street, 20 seconds for this phase, 20 seconds for this phase, and so on. And it will say, and you're allowed to give a 15-second green extension. And then it's the local controller that will actually do it. Yeah?
A near side stop means that the detector is just right there by the intersection.
Well, it means that the stop is just before the intersection. So if I put my detector, normally, let's say I want to give a 15-second extension, I locate my detector 15 seconds upstream of the traffic light. Well, what's 15 seconds ahead when there's a dwell time in there? So you know how random dwell times are, right? Are there going to be 1, 2, 5 people getting off? How many people are getting on? Maybe somebody who needs assistance or having trouble with their fares. And so because of that, we won't usually call for an extension if there's a stop in between because we don't know how long it's going to be. So near side stops, not entirely, but they get some benefit. You know, if the bus is pulling out 2 seconds of extension, that's nice, but it's only 2 seconds. So it nearly kills the effectiveness of green extension. So that's a reason, if you want to do transit priority, you review your route and you say, can I move the stops to the far side? There are a lot of other reasons to move stops to the far side. Transit agencies around the country are, where they can, are moving stops to the far side. So in the MBTA recently, they did a review of all their key routes. And one thing they looked at is, can we relocate stops? But they have criteria. You know, where there's a stop, there has to be, you know, a level landing place. There can't be, you know, fire hydrants and telephone poles in the way. It can't be driveways. So some of the streets that I've looked at for, could we do transit priority? And the first thing I would say, oh no, it's a near side stop. We got to move it to the other side of the street. But on the other side of the street, there's a driveway every 30 feet. You can't put a bus stop there. Or there's a firehouse. You can't put a bus stop there. So sometimes we're stuck with near side stops, and then green extension just ain't going to help us very much. Okay, before I go into more tactics, let me go through this list of common weaknesses in trying to do it. So one weakness that I've seen a lot here in the US is what I call cautious priority. So all this equipment they put in this transit priority system, but the traffic engineers are so afraid it's going to screw up traffic that they'll say, once we give priority to a bus, we inhibit the whole system for 5 minutes to give the signal a chance to recover. Or we inhibit at least for another cycle. Or if the cross street if the traffic level on the cross street is too much, just turn off the signal priority system. Okay, so the Silver Line running on Washington Street has a priority system. Some of the cross streets have so much traffic that they have this rule. If the cross street volume is too much, turn it off. Well, it's turned off. Okay, so the bus never gets priority at Melnia Cast. It never gets priority at Mass Ave. Many of the cross streets, the bus has the green light for like 70 out of 90 seconds in the cycle. So it's almost always green. So the bus almost never needs priority. So the priority, there is priority, but the benefit is very tiny. So in the end, what do you get? You get almost nothing. And then a second weakness is not thinking about the impact of priority on traffic and then unnecessarily hurting traffic, like not having a checkout detector that I mentioned. But the second bullet there, that's an important one I want you to think about, is compensation. Compensation is a key to making priority not hurt traffic so bad. And by compensation, what do I mean? What I mean is, if I'm going to give the bus street 15 seconds, I'm taking those 15 seconds away from somebody. Are you going to give it back? The language that traffic engineers use is they use the word borrow. They say, oh, we'll just borrow 15 seconds from phase 2. And then I ask, are you going to give it back? And they say, well, no. I say, well, then it's not borrowing. That's stealing. So if you take away 15 seconds from phase 2, and phase 2 in the next, now they can't clear its queue. And then, so now it's going to have a long queue, and then the traffic engineers will say, oh, no, now if we let them have priority in the next cycle as well, oh, no, what a disaster. So that's where you get these rules, like if we do priority, no priority for the next cycle or the next 5 minutes. But if I hold the light green for, let's say, East Street for the bus, so if I hold the light green in 15 seconds for East Street, who's going to get through in addition to the bus? A bunch of cars, right? A bunch of cars who otherwise would have been in the queue for the next cycle. So that means when we come around to the next cycle, East Street is not going to need as much green because some of their cars already got through. Meanwhile, other streets whose green we took, they need more green. So, hey, why not just be, reasonable and fair about it? Since we gave East Street some extra green, in the next cycle, we'll give the other streets extra green, and we'll take some away from East Street. That's compensation. That's a sensible way of doing things. And what you'll see is we don't do that. We can't do that with much of the standard way of controlling lights that we follow here in the US. So, and that's the inflexibility that I'll be explaining later on. Then we'll do, another weakness is we'll do the easy things. Green extension is easy, so we just do green extension. And then, like I said, if you have near side stops, well, you don't get any benefit. And there are other tactics that are harder to do, but we only do the easy ones. And then the last weakness is failing to collect data. In something like this, it's hard to get it right the first time. You need to do it, collect data, see, are my buses getting the priority they're supposed to? If they're not, make some fixes. Is car traffic doing all right? Are there places where huge queues are building up, and try to fix it? So take the objective seriously. So now I need to move away from transit priority and just tell you something about traffic signal control in general, because it's something that isn't covered in a lot of the standard transportation planning curriculum. So there are two basic paradigms for signal control. One is fully actuated, and the other is coordinated. So fully actuated, that's uncoordinated. With fully actuated, that means every approach I've got detectors. And the standard detector, it's a loop of copper in the street, a couple rounds, that goes to a box, and through the miracles of electromagnetism, if a vehicle drives over it, it induces a voltage, and you can pick up that voltage, and so you know there's a car there. Yeah? So there's a setting of how much of a voltage change is enough, because it has to become digital. It's either 0 or 1. So if we increase the sensitivity, then that'll detect a bike. But then the danger is it will also detect a car in the next lane over. So there's a trade-off there. So then we actually have, if we want to detect bikes, we use a figure 8 configuration, and then we try to educate the bicyclists, drive right down the middle of that figure 8, and that's where you'll get picked up the most. Hardly anybody knows that, though. There's another solution to bike detection, which is, if you're a bicyclist like me, I like green, I like red, I like yellow, I like all colors. I'll just go. So, all right, so with fully actuated control, I've got detectors, and based on those detectors, I will know how many seconds has it been since a car passed through, and gap. And once the gap reaches a certain threshold, 2.5 seconds, 3 seconds, then you have gapped out. Boom, your turn is over, and it's the next one's turn. So there's no fixed cycle length. Who knows? If traffic volume is light, we serve you, we serve the next, we serve the next, and now we're back. traffic is heavy, it might take 90 seconds to cycle around. But it's completely flexible like that. And if I interrupt something like that for transit priority, and now there's a longer queue. Okay, everybody's been waiting an extra 15 seconds because of this transit priority. Well, when their turn comes up, if they've got more cars, well, the detector will say, hey, they still have cars. Still have cars, yeah. Still have, keep them going, keep them going. Okay, now we finally have a gap. You're over. On to the next one. And if East Street, like I was saying, has less traffic, the street that the bus was on, because it got that green, when its turn comes up, instead of holding the light for 35 seconds like it usually does, it'll hold the light for 25 seconds and then say, I'm all done. No more traffic. So fully actuated control is a great background for priority because it's inherently flexible. It's cycle-free. It has that built-in compensation. But then there's another way of doing control, another basic paradigm for control, which is coordinated control. In the US, I'm showing the most kind of the basic paradigm, which is the dual ring with 8 phases. I'm not including right turns because right turns usually don't have their own lights. The right turns just go with the through movements. And with coordinated control like this, we have EBL, that means eastbound left, westbound through, WBT, westbound through. So the east-west street has its time. There's an upper ring and a lower ring, and the rings that are in parallel, they can move together. So when the light starts green, eastbound left and westbound left, 1 and 5, they're green together. What comes next, 2 or 6? That depends. Whichever one has more traffic, 1 or 5, that will stay green because it has detectors, while the other one gaps out. So maybe 5 gaps out first because it had less traffic. Then 6 becomes green along with 1. Eventually 1 gaps out. Now 6 is green along with 2. But then 6 and 2 have to end together. And then we have the same thing for the north-south street. So this could be fully actuated. But when I say it's coordinated, what I mean is phases 2 and 6, those are the coordinated phases. And the cycle goes from the end of 2 and 6 until the next end of 2 and 6. And that is a fixed amount of time. So if it's a 110-second cycle, it's always 110 seconds from this point till when it comes around again. These phases can have some actuation. They can have some detectors. And so they might run shorter than scheduled. And if they gap out quicker, run short, and this one gaps out, it runs short, this one gaps out, it runs short, that means 2 and 6 are going to start early. But if they start early, they never end early. They run their full length because that's how we have the full cycle. And the advantage to do that is when you have many signals in a line on an arterial and you want a green wave, you have them all on the same cycle, and then you have their differing offsets. So let's say signal 1, its green starts at time 0. The next one that's maybe 20 seconds away, well, its green starts at time 20. And that way, the cars can get a green wave. That's the idea. Yeah?
Are we assuming that all left turns on this are protected left turns?
Yeah, as I drew it here, it's protected left turns. You can have protected plus permitted. I mean, there are variations. You can if there might be no left turns, then you can just take them out. But that's the basic scheme. Now, what I want you to think about is, suppose the bus is on phase 2, which is a common case. That's your main street, the street that's coordinated. And the bus says, I need an extension. Extend the green. All right, we're going to borrow some time from the later phases. So we're going to hold the light green an extra 15 seconds. But remember, we are guaranteeing that at the end we've got to be on time again. So if now we've only got 85 seconds left to complete the cycle. And phase 2 and 6, they are not only guaranteed their ending time, they're also guaranteed their starting time. So that means we have to take those 15 seconds out of 3, 7, 4, 8, and 1, 5. So let's to make things simple, let's only look at the bottom ring. So I have to take 15 seconds. The first generation, they would take the whole 15 seconds out of phase 7, and then phase 7 would just get canceled. Well, that caused big problems. So now what they'll do is they'll proportionally take it out. So let's say phase 7 is normally scheduled to have 20 seconds, and this one's normally scheduled to have 30 seconds, and this one's normally scheduled to have 20 seconds, so 20, 30, 20. That sums up to, what, 70? So I'm taking 15 seconds out, so a portion of that I'd take from you, I'd take from you, I'd take from you. You get the idea. Is there any compensation going on here? None at all. Phase 6, the coordinated phase, got an extra 15 seconds. The competing phases, they all got cut short. And now phase 6 comes up for a full phase. That's the way our coordinated systems are programmed to work. They don't have to be programmed that way, but that's the way they are. I mean, if you buy them from any American supplier, that's how they're programmed to work. So when you say, let's add transit priority on top of that, now you can understand why the traffic engineers say, I don't know about a 30-second extension. Or, oh, after giving priority in one cycle, we better not give priority in the next, because it can really screw up traffic. It lacks this mechanism for compensation. And compensating would be easy. It would be, say, let's let 7 run for its full scheduled time, unless it gaps out. I mean, if it gaps out, if there's no traffic, don't. And allow 6 to start late, because 6 got some extra time. It probably doesn't need its full amount. But we don't do that. And then if we do a longer extension, we get out of coordination, we have to return back, and I won't go into that. Then I'll talk about a second tactic, and then I'm going to take a break so you can hear about how they've done priority in the Netherlands. A second tactic is early green. Okay, so in this diagram, the phase that's green, that's the phase in which the bus is coming. Okay, and the phases that precede it, those are competing phases, the cross street or left turns that are waiting. Okay, and the red dashed line, that's when in the cycle the bus is going to arrive. So I've got a situation where the bus is expected to arrive near the beginning of this left turn phase, and then it would have to wait through the end of the left turn phase, and finally its phase would be green. So with early green, I could truncate, I could shorten the left turn phase. I could even shorten the north-south phase before it, so that now it's a shorter wait until the bus's green comes up. Maybe I even skip the left turn. I shorten the through phase, skip the left turn, and really make things better for the bus that way. So an interesting way to look at early green compared to green extension, it's a small benefit, because if I make the green start 10 seconds early, that will reduce the delay for the bus by 10 seconds. Remember, with green extension, a 10-second extension could save a bus 90 seconds. But it's a small benefit, but who benefits? Any bus arriving on red, and red is usually a long time, and there's a large percentage of buses arrive on red. Actually, the early part of green buses can also benefit. So it's a small benefit to a large number of buses. Yeah?
For skip, you have the question marks. Why wouldn't you just flip the 2 cycles, flip the left and the...
Well, that's a great idea. So flipping them, but now then you have to give that tactic a different name. And that name is called phase rotation. So, yeah, and some people think phase rotation is an invitation to traffic Armageddon. It's going to be disaster. Cars are going to be smashing into each other because people expect their phase to come up at a certain time, and if it doesn't, they're going to think the light is broken and go through. This is something that can be tested.
Yeah, I was just going to ask whether, I think I've been in a light before where I had a skipped left turn and I was pretty pissed off.
So in Zurich, when the traffic signal programmers said, you know, we can give better priority if we can do this, the higher ups were worried about this. So they said, what we're going to do is we're going to have a campaign in which we're going to let the people in the city know that for the next 6 months, the sequence of traffic signals is going to be completely random. Just wait till your green comes up. And they did that. And then they went to having phase rotation.
Is the law that you're supposed to wait until the green light? And they're assuming people.
Yeah, but I mean, so in my life, and my life is a little longer than yours. So in my lifetime of being out on the streets, and you know, I do drive a car sometimes. Once I went through a red light because I waited like 2 whole cycles, and my phase never came up. So I figured the detector's broken, and there's no traffic around here anyway, so I'm going. So you know, people will do that now and then. So it doesn't happen often though. And but what you say about won't people wait? There's one class of people who won't wait, and that's called bicyclists. So you got to watch out for them. Think about their safety. Now, in practice, often you can't get much benefit from early green because whose green are you trying to cut short? If what you're trying to cut short is the cross streets green, the cross streets green is often determined by pedestrian needs, and we don't cut pedestrian phases. Pedestrians in transit, you know, we're on the same team. We don't want to hurt one to help the other because all of our transit passengers become pedestrians as soon as they get off the bus. So a lot of times you just can't do early green because you got a wide street. The cars need about 15 seconds of green to get through, but the pedestrians need 24 seconds. So the green light's 24 seconds. It's entirely because it's what the pedestrians need. You can't cut that short. So that's a practical issue that early green, there are limitations unless you can detect the bus really far in advance and cut something else short. So let me take a break now and introduce Alt-Tab. There we go. Introduce Jan Nederveen. Jan is a senior transportation planner with the city of Delft. And I get the privilege every summer for the last 10 years. I've been taking 20 or 25 Northeastern students to Delft for 5 weeks for a course in sustainable transportation. And there they get to enjoy incredible bike paths, incredible roundabouts, streets rebuilt to be safer, public transportation systems, new train station, fantastic stuff. And it turns out the guy who plans a lot of this stuff is sitting right here. And he often speaks to our students and explains to them the philosophy behind it. So, Jan, would you come and say something about how do you do transit priority in Delft?
Okay, welcome. Thank you for having me here. I'm going to tell you something that's work that I don't do, but my colleagues do. I've got 3 people in my department doing traffic engineering, traffic lights. They design it, they build it, and they maintain it. So what I show you here is part of what the thoughts they have done. And I only focus on public transport. Peter asked me many times to tell a lot about cycling, but this time it will be public transport. First, I give you some views about the network, and then I show you the 2 kinds of priority we give. We do physical priority, and we do time priority, and I show you some slides with some examples of Delft. First, our city Delft, 100,000 residents, closely to the city of The Hague with 600,000 residents. That's how we oriented in the busiest part, dense part of the Netherlands. And first we had one system that tried to serve everybody. And we didn't succeed in it because our public transport system was too slow. We tried, and then we figured out, oh, that's good. We have 2 kinds of groups we like to facilitate. One group are the commuters going to their work, and what they love is speed, as soon as possible going to destination. In their view, they only needs one stop in the front door and at the destination, and everything between is not needed for them. Well, I need to collect so more passengers that we say we make straight lines, few stops, serving high dense volume housing with high dense jobs together. And then we can cover a high speed, a high quality, and we see that we attract more passengers. The second group is everybody else, usually elderly people, people without a job, and we focus on them, as we say, they need the coverage. They have to go to many locations, so we make a citywide network covering every area, and that is located on a lower speed because we have to cover everything, a lower frequency, but that's the way we handle public transport. The first group is growing, the second group is stable, if you look at the data. This is how our network works. I've got a purple line. That's the Dutch railway system connecting all major cities of the Netherlands. If you get in Delft Central Station, within an hour you're standing on the central market in Amsterdam. Within 10 minutes to 15 minutes you're in Rotterdam or The Hague. Nationwide system, very good quality. 11 trains each hour, each direction. So it's perfect. If you live in Delft, you can reach 1 million jobs within 45 minutes. So if you need a place, live in Delft. That's our first system. The second one, if I ask to the people what do they like, most of the people like light rail, like tram. There's a large group of car drivers who love light rail and don't like buses. So I try to convert my complete network to light rail. That are the dotted lines over here. The red ones are already built, and we're still talking with the regional government to get funding for the black one. And if that's done, you see a spider kind of network covering most of the city. And I add some regional bus line through it, radial lines. That's the next coverage of our system, and that's the commuter network. And that's the last network covering everything. Step in a bus, pay $2, you get the whole city to view if you've got the time. That's the way how we cover the complete area. And the last group is transport on demand. If you're unable to use a public bus, you use smaller buses, you have to phone, and within 1 hour, such a bus comes driving through and you will picked up and delivered door-to-door transport. It's a fantastic system, but it's awful expensive. So what we're trying to do, get people out of this system, this marketing is growing, and get them then back in a normal bus. So we modify the bus so they are more attractive for people with light handicaps. And the other thing we are thinking about, maybe we can convert these kind of buses as a sort of timetable with a line structure for driving that kind of buses. So it looks like more public transport, which makes it more cheaper to run. Physical priority. That's the first thing we do. If a bus is in the same line as a car or as many bicycles, usually has the same speed and I cannot give him any priority. Let's give them bus lines. Where the center is, city center is, you see Delft, that is the downtown area, the central market square, that is where all the shops are and all the restaurants, that's the most historical center. It's a lovely place to be. You see a square over there, that is the central railroad station. If you'd like to leave the city, go there. And we designed all the bus lines going to the central railroad station. We can give them good priority on that location. When do we need a bus lane? We need it if there's a delay on driving with the cars. So in busy streets, I like to have a bus lane. And that's difficult because if it's a busy street, you need probably 4 lanes or 2 lanes of car traffic. And I'm asking 1 lane for 6 or 8 buses per hour each direction. So then we have to compete, but we said in the busiest areas, we start searching for a bus lane or a light rail lane so we can give them priority. And elsewhere, this is a residential area. It's nice to have, but you don't need to have it. This was thought in the 80s. Okay, let's make a bus lane everywhere So we get the bus lane in a residential area. And the only place we need it when he's crossing the highway on that and that locations, because that's our big intersections. Another part of priority is at the central station of Delft. This area, if you look at Delft and you take in Delft area, urban development, railroad, you see a huge development in the downtown area. Over here is the old station. Over there is the new one. We have spent 500 million euros to get the railroad tracks under the ground for 2 miles or 1.5 miles. And we built a complete railroad station, a new bus platform, and we did a complete separation of all the transport flows. On the surface level, we offered public transport. So in the open air, there's public transport. On -1, in the basement, we had a huge parking facility with parking lanes underground the bus platform. So we have a physical separations of the bike transport going to the railroad station and the bus transport. And on level -2, we had the railroad tracks. That's one way of separation. And you can see it here in the picture. This is the town hall, the class building, and the first floor, the ground floor, that's the railroad station with the name Delft on it. And underneath, in it white, you can see people standing at the entrance of the parking garage. We've got 100,000 people living in Delft. This parking garage for bicycles is today 8,000 places, and it's not enough. So a few years later, that will be 10,000 places for 100,000 residents. So bike parking is very important.
Yeah, but you also have a university there, so they're not all residents. Yeah, not all the students are residents at the university. I assume they
Yeah, it's students, it's also resident. No, yes, okay. But if you are when the students are at the university and you look at the parking facility, it's also full. And that are people leaving Delft. Some of them are also students going to a university in Leiden or in Rotterdam, but also normal people like myself are parking there. It's not a student parking garage. Yeah, but it's true that a large group of them are students. Well, -1, the bikes and the bus platform is operational on this level. So buses don't have to deal with cars or with pedestrians or with bikes. Yes?
The -1 is the parking for bikes. Do they also travel on that level, or do they go to the
The bikes also travel on -1. The bike lane is going here under this bridge and then entering the car. You can see there's a ramp over it. So we have a complete separation to -1 on the most busiest area. And that saves me a lot of time because the first traffic light, very close to the railroad station, should otherwise have to deal with 10,000 bicycles a day. But I offered them a tunnel, so I get a normal intersection with a normal traffic light. Otherwise, I cannot handle that amount of cyclists. And the speeder along this group, he will not stop. This is an aerial view of the system. The town hall is in the front. And we had also an east-west separation. On the inner city side, that's over here, we put the bus lane, the light rail lane, and on the other side we got the lane with the car traffic. And that was very important because on top of the picture, on the left side, I have an intersection where all public transport has to make all left and right turns. And that's the only one that makes the turns because the car road is blocked and the bike lane is underground in a tunnel. So I have an intersection where only public transport makes left and right turns. And on the other intersection is almost fallen off the picture on the right side. That is my car intersection where all the light rail traffic only has to cross. They go straight through. So it was much easier to handle if I separate public transport and car transport on different intersections. And my transport engineers who were interested in traffic lights, I took them, let me have a look at this design. Can you build a traffic light for this location? Because the alternative was one big crossing with everything, and that didn't work. I do also have some discussions with my urban planners, and they love the light rail in the green grass in the middle. And my public transport here likes to have asphalt. What do you like? I pick you out. Which one would you like and why?
I prefer the bike lanes because I feel like you're more in tune with, you experience the road better that way. And if you can serve the demand like that, then you should go green.
So which one do you like? The lighter in the green or the lighter in the asphalt? In the green. It's lovely. Nicer. Yeah. Well, we had a discussion also. I also think the top picture is the most beautiful. But it has one big disadvantage. If I have a bus lane or a public transport lane, but I like to operate buses as well as light rail, in this situation, they can both use the same line, and I get one platform, and you can decide if I take a bus or a light rail. And the one on top, if I like to add the bus lane, well, that should be a bus stop without priority on the normal street. I agreed on that one because I didn't have a bus lane anymore, because I replaced it by a light rail. Yes?
So what is like the typical frequency of light rail lines?
A minimum is 4 light rail vehicles an hour each direction. That's the minimum.
Yeah.
Otherwise, it goes up to 6 or 8 in Delft. And in other cities it can be more. But 8 is all pretty much for a city with 100,000 people. And he has to compete with cycling. So many people who cycle, you take them out from the public transport system. These guys, cab drivers, always ask me for, may I use your bus lanes? Because they are so fast. And they have beautiful traffic lights. I couldn't find a letter size bigger than this one, otherwise I said, no, absolutely not. I've got maybe 20 cabs in Delft, but it's no, no.
It's not more efficient than driving.
Oh, they love to drive my bus lanes like the fire department does. It's pretty fast, but no way I want it. Because if they enter a huge intersection and there is a bus going at that intersection, I know that bus will make a left turn. Because every bus on that intersection will make a left turn. And that means all other directions can get green. I don't know where that cab is going. So you have to completely block the intersection for one cab. Yes?
Why is it that London lets taxis use the bus lanes? Are you familiar?
In London?
Yeah.
Yeah, maybe they are block out all the other directions to give them the priority. And that will seriously harm all other modes of transport. It harm car traffic and bike traffic. And we like to give priority to the buses with many people. But this is one taxi with maybe 1 or 2 people inside it. That's not worth the effort. And it's a big risk to give him green and see what is happening. Time priority. Peter already taught some things. But this is what we do. We have special traffic lights, the 9 eyes traffic lights. That's in the picture on the black-white polar column. That's showing if you get green to left or to right or straight through for a bus. And we have 2 kinds of detection. The first one is the intelligent one. So every vehicle says, I'm bus 24, vehicle number so, I should be here 20 minutes past 5. So he's also telling his time per table. And then we know, okay, you're 1 minute early, we will not give you priority. That's the expensive one. And the other one, that's a simple detection. Some vehicle is crossing a detector and notice, oh, this is a vehicle. I even don't know which bus it is, even if you are a car, you are detected. And then you get some priority. That's the way of detection. The top one is the best. So if we are in charge, since our traffic light We put in the intelligent one. If somebody else doing the design, a regional government, sometimes we get the cheap one. Especially in the Delft University top technology campus, the cheap one is installed. Traffic light priority. Peter showed you a bus stop close to an intersection. Well, here's an example of a traffic light priority at a huge intersection. The tram has to make a turn to the left. And what we do, we put it 2 stop lines. The first one is the location where the light rail, the tram, has to stop for handling the passengers. I don't know how long that will take. And I don't want to stop all the other traffic because he is still handling passengers. If I do so, I get many letters from people waiting for nothing. So there's a second stop line, straightforward on the intersection, and then the light rail will tell, hey, hello, I'm here. Please, can you give me what priority? And what this system does, he will not break off all the other signals. He says, oh, I finished my phase. I then add in a phase with public transport, and then I continue with all the rest. I don't take out any time from the others, just I merge in a priority for the traffic lights. So this intersection has 4 phases, so there are 4 chances to give him priority. So the waiting time is not the full cycle, but only a quarter of it. That's how it works. This is the same intersection from the air. So it's a huge one, the biggest intersection we have in the built-up area. We have total detection, all directions, also the cycles they are detected with a detector. We don't use an 8, we have got a good detector. So we detect bikes. You also make a button if you like, but most of the time you're already detected. We have a fixed sequence which groups go together and what the sequence is. We have defined a maximum green time, what might be possible for each direction, and we stop giving green if we achieve a free flow situation. So I don't give green to free flow traffic. And if the traffic still contacts us a certain amount of time, we say, okay, now it's enough, all the others have to go. We have bus priority and light rail priority and fire truck priority. And we don't build intersections in Delft with a traffic light sequence of 120 seconds. That's the max. So if the area is congested, the maximum cycle time, 120 seconds. And my colleague said, if you look at our intersections, I'm trying to bring back the cycle time for as many intersections back to 90 seconds. And they did, and for most intersections it worked, and it was a huge benefit for everybody, but it saves the maximum waiting time, it's reduced 30 seconds. So if you missed green the first 30 seconds, just simply reducing the cycle time. And you can also do it physically, make your intersection smaller. That's a huge benefit for the cycling time. And we noticed some intersections were pretty sharp, 90 seconds. People get used to it, so they didn't miss the first second of green. They were green, check, driving. So we could handle the same number of cars in a shorter green time. Special one is the fire truck priority. The fire department has a depot exactly on that intersection, and they've got a beautiful red button. So if they press that red button, the intersection will stand in a way that the older directions are blocked, that the fire department has to cross. So if you're not in the direction of a fire that the fire department has to go, you still get green, because it is an intelligence red button. So I press this button, so I have a fire in Delft North, and I will follow this route. Then that route will get green for the fire truck on the time we think he will be there. So while driving north, he is continuously detected, and the traffic lights are switched that way that he will get green. We do not block completely all these intersections for the fire trucks, but he knows that if we do so, we might cause a traffic jam because all the directions are blocked. And that's the way how we cater. And we also detect if he pressed the right button, and if we have a make a system that is going perfectly to the north. I mean, he didn't use that route. At a certain time, the system arguments, okay, I didn't measure his somebody has disappeared or gone somewhere else, but let's switch back to normal. That's the fire priority we've got in Delft. And it was very important when we built the railroad tunnel, because the whole area was constructed, under construction, but all the traffic lights keep to that priority. And that's an example from Delft. Thank you.
My new graphic, get up there. Yeah.
Don't worry.
Yeah, so so I told you that tactics are green extension, which is great if you've got a far side stop and you can predict in advance. Early green, which is a little more limited, but we need more flexibility. So like what Jan was describing there, they had these four phases in the cycle. To make it simple, let's just say we have east and west left, and then east and west through, and then north and south left, and north and south through. Phase 1, 2, 3, 4. And the tram, in this case, because it actually conflicts with all of them. So the normal thinking of a traffic engineer would be, okay, and then we'll have a tram phase here. And now that's the cycle. But the Delft thinking is, we'll put a tram phase here, we'll put a tram phase here, we'll put a tram phase here, and a tram phase here. And if there's no tram, well, we skip it. And if there is a tram, then the tram gets to go. So the tram never has to wait long. So that's part of the, if we can get a man on the moon, we can turn the light green. So let me say something. I'll leave the rest of these slides. They have some details there. But let me tell you something about D Street and the Silver Line. Okay? So the Silver Line is the waterfront Silver Line. Huh? No, I'm not going to do the video. This is something new. How many of you are familiar with the Silver Line that goes to and from the airport? Yeah. And you've seen it at D Street is where it comes, if you're going toward the airport, it comes out of the tunnel and then it stops at a red light. And while you're waiting at the red light, you can watch, and there's no cars going by. And then why is the light red? So on a map, here's Congress Street. This is D Street. And then this is Silver Line Way. So the traffic engineers are concerned that that's a short distance. And if they turn the light red for Congress Street, two bad things can happen. One is spillback. Traffic comes to here, oh, the light is red, and our queue spills back, and it hurts the capacity. And the second one is starvation. The light turns green here for northbound traffic, but the light is still red here. So cars start to go, but nobody can go because they're stuck. It's starved. So they don't want to close D Street while either of those things can happen. So there's a cycle. It's a 120-second cycle. This time I'll draw the cycle in a circle. And they've decided, here's the time in the cycle the bus can go. So that's why you just wait. You just wait. You arrive, and you just wait until your time in the cycle. So I just recently had some students study it in my advanced traffic control class. We actually took the whole class there for a field trip during the morning peak hour because I had to see it myself. Is it really the disaster people talk about? It is not a traffic disaster. It is a transit disaster. Because the frequency of the Silver Line, it's about one bus every 2 minutes, and they go in both directions. So that means in a 120-second cycle, if they're perfectly on schedule, you'd have one bus, at most one per direction, but of course they're not. So often you've got two buses, sometimes three buses waiting to go. And they wait, and they wait, and they wait, and they wait. And most of the time there is no conflicting traffic. So my students learn how to do traffic simulations. There's some standard packages for that. They learn how to program their own traffic control. And they said, let's try just all-out aggressive priority. When we detect a bus, we just stop the street, let the bus go through. The bus only needs like 14 seconds, and then it goes back. And I can hear people saying, oh, but sometimes you got to serve 2 or 3 buses. Yeah, when your buses have to wait 2 minutes till their turn comes. But when they don't have to wait, you're never going to be serving more than 1 at a time, and it only takes 15 seconds. We put that into the simulation to see, okay, how is it going to affect cars? How is it going to affect buses? Average delay for bus goes from 50 seconds down to 4 seconds. Why 4? And that's only because if we do turn the light green for a bus, for the cars, we a minimum 20 seconds before the next bus. So if a bus in one direction, the bus coming in the other direction, 15 seconds later might have to wait a few seconds. So delay for bus goes down to almost 0. Delay for cars also goes down. Because the system they have now will stop the cars even when there's no bus. I don't know why. And there's another thing about the system they have now that is not so intelligent. So the main message I want to get across is the old way I said it is if we can put a man on the moon, we can get the light to turn green for the bus. That is if we use intelligent tactics, we can almost always reduce the delay for bus down to near 0 without really increasing the delay for cars. Bus only needs a few seconds to get through. They just need the few seconds at the right time. Just to rearrange the time a little bit. Give the bus the green when it needs. And what's in the way is this inflexible paradigm of fixed time control with a fixed cycle and long fixed cycles. Like Jan was saying, the long cycles are killer. If you have short cycles, the delay won't be too much. So, what Europe has done with transit priority is just amazing. Some of the things that I saw there, it just blew my mind. How they're just giving priority to transit. They just do it. They just do it. They just do it. There was an intersection in The Hague, right near Delft, where a tram line was intersecting the main ring road. Lots of traffic. And big traffic jams. And my friends are telling me, oh yeah, big traffic jams here. How come? Well, because we have to give the tram priority. I mean, it's like, you just have to. You drink coffee in the morning and you give the tram priority. That's who would ever think of making the tram wait at a red light? No, you have to give the tram priority, and there are lots of trams, and it's causing a big traffic jam. So what's the solution? Spend a lot of money, grade separation, and now the tram has absolutely 0 delay, and the cars go underneath and they have no delay either, and everybody's happy. But it started because of this attitude that we just give priority to our important transit lines. So if we have that attitude, we can do it a lot better than what we're doing.